Welcome to Master of Science with host Professor James McAnee. The good professor's career spans 50 years as a university teacher, scientist, and engineer. Each week, he will explore the rapidly changing world of science as many long-held theories are crumbling under the weight of new data. He will cover the fields of geology, archaeology, meteorology, oceanography, space science, astronomy, cosmology, biological evolution, virology, energy, mathematics, and more. So please welcome the host of Master of Science, James McAnee.
And good evening, everybody. This episode 37. We're moving along. This is going to go on for a long time. It's very interesting. It's getting a lot of support and increasing numbers every week. So tell your friends. And as I say, tell your people you don't like to watch the show. They might become your friends. Tonight, I first want to talk about circular reasoning. Every week I try and discuss something that's going on in science that is backwards and out of place in a scientific world. The way science should work now, there's the simple version of the scientific method. You make a hypothesis, you test the hypothesis. And back in the old days, things were much simpler. Now we have hypotheses that are literally impossible to test. Let's give you an example. How about the observation, which is an observation that when comets come into the solar system, they have finite orbits. In other words, they very rarely does a comet come into the solar system with the open orbit, which means it comes in and goes out and never comes back. The majority have a limit, but it's way out there. And that's where the birth of the concept of the Oort cloud came from. It's from scientists that realized that the orbits of comets, which are these wanderers from afar, have limits the outer range of their orbits, and it tends to be at a certain place. And so they said, okay, well, that must mean that since they believed comets were dirty snowballs, this is going way back to Kepler, who originated this idea that comets were things that melted when near the sun. An idea that's totally patently false now that we've landed on the nucleus of comets. And there's no water, there's no ice, there's no snow, there's nothing coming off the nucleus. It's a hot, dry rock, and it's discharging the solar capacitor, and that's what causes the tail and all the other effects that we see, in addition to a lot of other effects. But at any rate, back to the concept of the Oort cloud. So they hypothesized something that is in all, if you look in any astronomy textbook, there will be mention of the Oort cloud as if it were fact, this so-called cloud of comets that's way out there. The only problem is, in the real scientific world, in the world of real science, it's not verifiable. Because, first of all, the spacecraft that has gone the farthest, the Voyager spacecraft, has just barely gotten outside of the realm of our own star. Certainly nowhere near the region where this Oort cloud, this hypothesized Oort cloud, would be. And even if you could get a single spacecraft out there, then you wouldn't be able to see this whole immense region of space that supposedly is filled with little ice balls. And additionally, they're so small that you'd have to be really close to them even to see them. And out there, it's pitch dark. There's no sunlight to reflect off something to give you a visual. And they're cold, so, I mean, your infrared wouldn't work. Your infrared cameras would not work. So it's literally something that is unverifiable in the true scientific sense. And so it's an assumption, but it's treated because it's so necessary to support the other bogus theories that are floating around today. So I want to talk about something called circular reasoning. You make an assumption, and this is kind of where the where the scientific method goes wrong. You make an assumption, you do experiments, and this would be, like I say, in the old days, you could do experiments in the laboratory and prove them. For example, let me give you an example of dealing with gravity. There's all kinds of hypotheses about, oh, gravity is electric or something like that. No, gravity is not electric. And the reason being is that electric things can be shielded. You can build a shielding grid or other methods of shielding magnetic and electric fields so that they don't propagate past a certain distance. For example, now the big rage is these little cards that somebody can walk up to you and scan your credit card in your pocket, take all your information, take your money, and scan it at a distance. So what they do is they put a blocking card in along with your other credit cards to block the electromagnetic signals from getting to your credit card. So at any rate, that's just an example of electromagnetic fields. They can be blocked. Gravity, however, cannot be blocked. It's very interesting. And so gravity does not follow the basic properties of electromagnetism. Okay, so there's an experiment. I've done this in the laboratory as an undergrad. In the physics department, we had what was called the Cavendish balance. It's a very delicate balance, and what it is would be a wire, a very thin wire that hangs down from a rack, and then on there you have a heavy ball, or a pendulum with a stick and a ball and a weight or something like that. And at any rate, it's then you take another large gravitational object mass, you put it near there, and you can actually measure the force of gravity in the laboratory. Just a very simple experiment. So you can prove gravity as we know it. It's not electric, it's not magnetic. And you could put a electromagnetic shielding between the two balls on the Cavendish balance, and it would still work. You cannot shield gravity. Okay, so that would be a type of an experiment. Or another one, let's talk about measuring the charge on an electron. The charge on an electron, there's various experiments that allow you to measure the charge, the quantum charges on an electron. And I've done that experiment in the laboratory and came out with very good results showing, literally measuring the charge on an electron. So those are in-laboratory experiments, very simple to do, not so terribly simple, but basic. Something certainly an undergraduate can do and get the results and understand actually make significant measurements that are very accurate. But and so the scientific would say, okay, you hypothesize a quantum charge on an electron, you measure it, then someone else, here's a key part to this, a very key part to scientific method, is that independent third-party verification. In other words, somebody off in another country sets up the same laboratory experiment as you had, and they can make the same measurements, and therefore they are able to verify your results, and then somebody else does it, and the more people that do this, they go, yeah, that's right. Charge on the electron is such and such. The gravitational constant is such and such. You can measure this by knowing the properties of the ball in the Cavendish experiment and Cavendish balance, etc. But then you come back and you say, okay, now you can write a theory and you can quantify it, but there's always a chance that might be modified or qualified in the future. So it's a progressive steps, but that's the scientific method. But what if you cannot prove the hypothesis? What if it's unprovable simply because of the physical situation? You have a little problem. And you have a bigger problem when people start assuming that they start, okay, so they hypothesize the Oort cloud, and they measure the orbits of comets, and yeah, all these comets seem to fit that pattern. And And then they verify the concept of the Oort cloud by circumstantial evidence. This is evidence that would not hold up in a court of law at all. So the judge would say, well, okay, that's very good. That's all circumstantial evidence, but where's the direct measurement? Where's the evidence from the scene of the crime? And with the Oort cloud, there isn't any. You couldn't, and you can't imagine, even with advancements in space technology and rocketry and traveling through space, and there's no way you can measure the Oort cloud. There's no way you can get a measuring stick or a meter or any other type of measurement out there to measure the Oort cloud. So this is where the problem in science, astronomy, especially astronomy, and astrophysics and space science comes in. And they use circular reasoning. So what happens, they build a case. They build circumstantial evidence and more circumstantial evidence and more circumstantial evidence. And all of a sudden the case becomes, and they start using it as a crutch for the other theories, and all of a sudden they can't change it. Now it's ingrained in the theoretical structure, and it has to stay there. This is what I call circular reasoning. So let's take some other examples. The Big Bang is like, now there are more and more people, thank goodness, are coming out. And I have published papers on this myself, now, some not so long ago, dealing with the fact that the Big Bang literally is junk science. It should have never, ever gotten the footage, that it should have never gotten the traction that it has obtained in over 100 years. And there again, you look at redshifts, okay, everything you look out in the universe is redshifted, which if there was only one redshift, cause of redshift, then that would imply that things are moving away and the universe is expanding. But how do you take that then and extrapolate it back in time to a point no bigger than a pinhead? That's a pretty big order. There's no evidence between today and that pinpoint. I mean, that's an assumption. That's a very, very, very big assumption. And there's no proof for it. Where is the proof? Well, I'd like to meet the guy that's proved that one, because, but what they're doing today, of course, with the James Webb Telescope is to show that there are well-developed galaxies right there where the Big Bang supposedly happened. And by the way, if this happened, if the Big Bang happened in this pinhead little spot in the universe, then we should be able to look at it and not see galaxies in all directions. The early galaxies should be all pretty near that place, shouldn't they? But we look around with the James Webb Telescope or other telescopes like the Euclid, and we see galaxies in all directions. Well, wait a minute. They shouldn't be in all directions. The only ones that should be that far away, using the redshift and the Hubble constant to measure distance, the only ones that should be in existence at that period of time, just after the Big Bang, should be right there, concentrated in one spot in the sky. And that's not what we see. There's all kinds of other problems with that, because if the light has been coming to us for those billions of years, how did we get that far away this fast? So the light is just catching us right now. We would have had to gone faster than the speed of light. It's like, since everything came out of the Big Bang at the same time, and since we're looking back in time, seeing this stuff billions of years ago, 13, 12 billion years ago, that means we had to run. Let's take a simple example. Let us take a simple example. You're waiting at a bus stop, okay? And all of a sudden, all the buses leave the bus stop at the same time, and you're right there where the bus stop is. Now, you want to catch your bus, but the bus is you can't meet it right there. You have to go up to a different place to catch the bus. So you run really fast and you get up to that place, and then the bus catches up to you. The bus moving, of course, at the speed of light. Well, wait a minute. You had to move faster than the speed of light to get to where you were to then wait for the bus, right? And this is the quandary of the Big Bang. And here you have physicists who don't think there's a problem here. Excuse me, how did we on planet Earth get so far away from the center of the Big Bang that we're looking back in time 12 billion years at galaxies that formed during the Big Bang? We had to move pretty quickly to get out to where we are today, much faster than the speed of light, so that the speed of light the light coming from these galaxies could then catch up to us. Doesn't that pose a little bit of a problem? It would for my way of thinking. Anyway, okay. So what you have is circular reasoning. And so the hypothesis, instead of the scientific method, which is hypothesis, experiment, verification, theory, and then back to the hypothesis loop, and that would be the scientific method. What's happening today is circular reasoning. Hypothesis, third-party what you might call tertiary evidence, third-level evidence, and then all of this supporting evidence builds up, and then somehow, verifies the theory. People get Nobel Prizes. Isn't that special? Get funding. Okay, another one is climate change. That's one in which where I love this expression that 95% of scientists agree on climate change. That's what the expression is. But you have to understand, the people that disagreed lost their funding, lost their publications, were booted out, and the only people left were the ones smart enough, if you call it that, smart enough to realize that the money comes from saying yes. And so ultimately, all these scientists standing in a row agree, and the funding keeps coming in. Isn't life good? But there again, circular reasoning. And the problem with science of climate change is that it's not direct measurements. And you might think, the temperature rise is what tells us that the world is heating up. Temperature and heat are two different things. And I often use this example. Here's an example of the quandary of climate change. Take two boxes, put them on a table, exactly the same boxes, the same air content, the same volume of air, all of the identical, the air that's in the two boxes. Okay, and they're at exactly the same temperature. So you put a thermometer in there, they are exactly the same temperature, all exactly identical. Now, in one of the boxes, you add some water vapor. Okay? You add some water vapor, that's the only thing you do. And now, lower the temperature in that container. Its temperature is lower, but it has more heat content because of the water vapor. So there's more heat in the box with the lower temperature, whereas the box with the higher temperature has less energy. And so measuring temperature or predicting temperature is not a measure of climate change at all, or of heat content. So they're saying the heating of the atmosphere, heat is energy. That's one term. Temperature is something very different. And as I always say, if you want to know what the temperature is going to be, if the wind's from the north, it's colder. If the wind's from the south, it's warmer. And they don't measure all over the globe. Like I mentioned last week, they will put the thermometer out at the airport where it's always a few degrees warmer. Well, gee, guess what? You're going to measure climate change, or are you just measuring that the airport has warmer temperatures? Report it like it is. But there again, the idea of circular reasoning. You make a hypothesis, you gather all this data, the data seems to support your hypothesis, and then it becomes a proven hypothesis. But here's the crux in the modern world of science, that the funding, which comes from the federal government, comes in a top-down manner. Now, here's the way funding works. If you're a scientist, you don't think of an idea and say, this is what I want to research, and I'm going to go get a government grant to research this. No. You go pick up a book, which is a catalog of all of the grant propositions, all of the subjects that they want studied for this year. It might be the National Science Foundation, National Institute of Health, and on and on and on. And I've seen when I was in grad school, I saw my professor going through the catalogs looking, can we do this one? Can we do this one? And then they go, he had an expression. They called it quick and dirty. And so what it was to do an experiment quickly, get some results, put it in, and say you got some basic results to get the grant money. So anyway, this is what scientists do. And it's, like I said, it's like squirrels that forgot how to forage. They're not there to try and advance science. They're there to find the grant money and apply for it and get the grant money. And then just guess what? After a year, 2 years of the research, spending that grant money, they're going to come up with a positive result, I guarantee you. And when they get that positive result, then the inspector comes out from the agency, the government agency, to see the results. And they might be very hard-nosed about it, but ultimately they're going to renew that because that's their job. Their job is to see progress in the scientific community, which is based on them giving out this grant. It wouldn't look good. What would it look like if they went out, the inspectors, after 2 years, they go out and inspect the university laboratory where this experiment is going on, and none of them worked, and all the data was fudged, and it wouldn't look good. So it's in their best interest also to approve and keep these grants going and extend the grants. So it's like a system. It's like a system that is based on funding and keep the funding rolling. And much of this is based on circular reasoning and not good science. Okay, so I could go on and on about another good example you see all the time is scientists talking about the birth of the solar system 4.5 billion years ago, they say. There's no evidence for that, not a shred. But it's one of those nursery rhymes that if they keep repeating it, then everybody's in agreement and life is good. And the reality is that the planets are all different ages. They are completely different ages. And the real formation of the solar system is done by something called capture. My original book when I was at Cornell was dealing with the comet capture processes in the formation of solar systems and how large comets attract matter because of the discharge of the solar capacitor and then build up and become planets. We in fact have a planet forming right now in the solar system. Most people don't know about it. We call it Hale-Bopp, the comet Hale-Bopp. It's growing, it's becoming bigger, and it's going to be back in about 2,500 years. None of us will be around to see it. But there's a probability that it will interact with some of the planets and start becoming a planet in the inner solar system. Okay, so at any rate, now this brings up a very interesting topic, and this is one of the mathematics topics. I'm a mathematician also. I have some amazing discoveries in the realm of prime numbers. I worked for 25 years in the computer industry, and one of my specialties was encryption, which is mathematical processes. My first 10 years in the computer industry, telecommunications, was dealing with a group, and we did modeling, computer modeling and the mathematical analysis of computer networks and understanding the ebb and flow of movement of data in networks, because we were building network processors that move data in the computer networks. Okay, so at any rate, I have fairly good background in mathematics, both from student. I have a double major. My college major is double major in physics and mathematics. So I had a complete major in physics, a complete major in mathematics. And that's, by the way, something that most physicists, astrophysicists, space scientists, and astronomers do not have. And this next example will be a good illumination of that. There is an expression in astronomy. And this comes from way back. One of the fundamental questions in astronomy is the universe infinite? Does it go on and on and on? Or does it stop at some place? Or is it finite? from the universe that we're in. And people talk about, by the way, I hear this all the time, parallel universes. Believe me, we're having enough trouble understanding the universe we live in. So anybody that talks about parallel universes, you know, send them out to pasture, please. If they want to talk about it, fine, but on your own nickel. Don't take tax-supported money to talk about parallel universes, please. But anyway, one of the questions in astronomy is a legitimate question, is if there was an infinite universe, and this is, like I say, a philosophical kind of a thought experiment, if there were an infinite universe, then wouldn't there be a star in every spot in the heavens, and the entire heavens would be aglow, and we would have no day and night? We would just have this light coming from every place, because every line of sight would end at a star. That's the belief. And then they say, well, because that doesn't happen, we look up and we see this beautiful night sky with nothing in it. Basically, we can, with the naked eye, we can see about 3,000 stars. If you're out in the darkest place on the planet, and you look up and you see just the sky is ablaze with stars, then you can see about 3,000 stars. That's what the human eye can see. And by the way, if you were out in space, you would not have the dispersion that goes on in the atmosphere that makes the stars look bigger than they actually are. Okay, so anyway, let's talk about this question a little bit. And so the people at the Big Bang, they claim that, oh, this is proof of the Big Bang, that the universe is finite, there's an end to it that began in a Big Bang. Well, not really. But let's just, when you take a physics problem, what you do is you go to the extremes. You try and analyze this and ask a few basic questions. And the first one I would ask is, well, what if there was an infinite universe and there were an infinite number of stars, therefore, because the stars are filling the space out there. But what if all the stars were all lined up in one line, and every couple hundred, maybe every 5 light years, there's a star. But they're all lined up in a line, perfectly in a line, so you'll only see one star, even though there's an infinite number of them. Well, you'd think, wow, that's true. So what it comes down to is understanding the density of stars. Not only is there an infinite number of them, but where are they? If they're all in one line, then there's an infinite number of them, but not every line of sight is going to end at a star, because there's only one line of sight. They're all in a big row. So it'd be like an infinite number line in one direction, just going out into space. All the stars are on that line, and the closest one would then be the biggest one, or someplace there would be one that overshadows all of them. And that's all you would see. There would be one star in the sky from your vantage point. Well, that breaks down that idea pretty quickly. But let's imagine that the stars are evenly distributed. And that, by the way, is an underlying assumption of this antiquated belief that if the universe were infinite, then every line of sight would end on a star. It's simply not true, and I'll be talking about some other examples here, but imagine a celestial sphere. Here you are, let's say you're on Earth or you're out in space, and you look up, and around you, just imagine there's a sphere, a perfect sphere, and let's put it at, let's say the distance of the sun, 93 million miles away. There's a sphere that goes around Earth, and let's pretend that there are enough stars covering that sphere so that there's a star covering every square inch, every square kilometer, every square mile of that celestial sphere. So it would take the sun and many more like the sun, and maybe little ones or bigger ones, all covering that sphere. So there wasn't a square inch that was not ending on the surface of one of these stars. Okay, well, then that would be the situation, that you would have light coming at you from all directions, and there would be no shadows because light would be evenly arriving from all different directions. And there would be no nighttime, there would be no daytime, there wouldn't be any difference between day and night, it would be daytime all the time. Okay, so now what if you took all of these stars, and let's say they're perfectly covering the area but with no extra overlap to spare. Move all of these stars twice the distance away. Now what happens? Okay, well, since you move twice as far away, the sphere that you're now surrounding you, the sphere that was 1 AU, astronomical unit, the distance to the sun, now it's 2 astronomical units, and so the area on that sphere is 4 times as much. So if you triple the distance of your sphere, then you would have 3 squared or 9 times as much surface area on your sphere, and you would need 9 times as many stars to cover that sphere as you did the original one. And if it went 4 times, if you expanded your sphere to 4 times the distance to the sphere, then you would need 16 times as many stars. So what you're seeing here is that the relationship between covering the entire sphere, what you call your celestial sphere, with stars, so that all lines of sight end on the surface of a star, depends not only on the number of stars, but where they are, the distribution of these stars. So if we assume that the stars are distributed evenly amongst the heavens, now we have a thing that comes into play here, and it comes back to something called infinities. And for example, I took a course when I was in undergraduate school. It was a course on infinities by George Cantor. And he was a mathematician who developed the concepts of infinity. For example, if you count 1, 2, 3, 4, 5 out to infinity, then there is an infinite number of numbers. But between any 2 integers, 1, 2, 3, 4, between any of those, you will have an infinite number of rational numbers. Those are fractions like 2/3 or 5/7. And there's an infinite number of those, but it doesn't completely cover the number line. Very interesting. But there's an infinity that is a bigger infinity of rational numbers than there is of counting numbers or integers. And then if you look at the real number system, between any 2 rational numbers, there's an infinite number of real numbers. And so there's different layers of infinity, different levels of infinity. And so this also comes back to a whole branch of mathematics called convergent and divergent series. For example, if you add up the sum 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, like that, out to infinity, that series diverges. And you might think, well, yeah, you're adding an infinite number of fractions. It should become infinite, because you're adding an infinite number of things. And this is related to the star issue. But if you add up the numbers 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, like that, and continue out to infinity, that series converges. It does not add up to an infinite number, and that's a convergent series in mathematics, and there's all kinds of convergent series. It's a very large branch of mathematics, and took literally hundreds of years for mathematicians to work all of this out and understand that if you add an infinite number of things, it doesn't necessarily add up to an infinity. You do not get an infinite result. They're called convergent series. And this is the same situation with the stars in the sky. If you have a distribution of stars that is beyond a certain limit, then you can have an infinite number of stars, but not every line of sight will add up will end at a star. And it's simply a matter of mathematics. So if the stars are sufficiently far apart, then you'll have dark skies. It'll be dark. Another thing that factors into this, which I should mention, is the reality of the eye or the receptor or the camera or the telescope you're using, that it has a resolution. And beyond that resolution, it's not going to see anything. For example, the human eye, as I said, would have 3,000 stars in the sky. If you looked up with the naked eye, looked up at a dark night up in the sky, and where it was perfectly dark, Arizona desert, or some places where it's very cold, it can be very clear also, and you look up, your eye can see about 3,000 stars. If you had a telescope, you would see many more. Why? Because it has resolution. It has the ability to go into a smaller area and bring that back to your eye, which is a sensor. If you put a camera, a digital or the old analog type of film, onto a camera, onto a telescope, then you can get more pixelation and you can pick up more detail. And that's what they're doing now with these orbiting telescopes. Just amazing results. But there again, the problem with these orbiting telescopes is the telescope time is owned and operated by people who are favorable to the Big Bang Theory. And so they squeeze out everybody else. They make a monopoly. I'm getting off the track here, but I just want to point that out. But back to the idea, is there an infinite number, if there's an infinite number of stars in the sky, should there be this glow in the sky that covers the entire sky? Now let's take a look at something else. It's called the Milky Way. This is our galaxy. So looking out in a certain direction, we're looking down the plane of the Milky Way galaxy. And you look up in the night sky, and there you see a big band of light stretching across the sky. And this is a case where the stars are close enough such that, the sky is pretty much lit up. It's not perfectly lit up, but pretty much. And if you look with a telescope, you can see gaps in that, in the arms of the Milky Way galaxy. But if you look, you have to remember, we live out what I would call in the boondocks in the galaxy. So we have a beautiful dark sky, and the only thing we might have is our own moon in the night sky to ruin the viewing. But we have a beautiful view of this entire universe. But if you were a being that lived farther in towards the center of the galaxy, there are commodities called star clusters. A star cluster is hundreds, sometimes thousands of stars that are clustered together, and they're all moving in the Milky Way, far enough apart where they're not colliding into one another. But if you lived in a star cluster, you would look up in the night sky, and you wouldn't see the beautiful universe that we see from this point of view. You would have light coming at you literally from all directions, because you would have thousands of stars up in the sky nearby, and they probably developed space travel and interstellar travel much sooner than we would, because our closest star is quite far away. Their stars are much closer. So like I say, they're moving in the galactic arm. But they are closer to the situation, and of course they're embedded farther in the galactic arm, so their night sky is not like ours. They would have to get outside of their atmosphere to get some kind of a glimpse, and then block the light from all of these stars to get a glimpse of what the universe looks like. And so at any rate, there is a situation where the star clusters farther in the galaxy would have somewhat this situation where the light would be there ever present, day and night, and they wouldn't have nighttime. So, but getting back to the mathematical model, you could set up a mathematical model. This would be an interesting project for students, is to determine the distance. And there's all kinds of things like this in mathematics, that if the stars were within a certain distance and of a certain size and number, then there would be light coming from, they would be within the limit where you would have light coming from all directions. In other words, light, any line of sight would end on a star. If you were beyond this limit, then you would not have every line of sight ending on a star, even though you would have an infinite number of stars. So this is a very interesting mathematics problem, but it's one that, by the way, the stars are very far apart. The galaxies are extremely far apart. Given the size of the galaxies, it's not like they're all bunched together side by side throughout the universe. Even there, you would have these amazing clusters of billions of stars and still be able to see through them. So once again, just to review, sometimes these concepts seem self-evident, like the Oort cloud. Oh, it's got to be there. Where else would comets come from? Let me jump back to there, and before I'll just finish this thought about the stars, the infinite number of stars in heaven. So it comes out to be similar to a mathematical problem, either a divergent, in which there's an infinite amount of light coming. In other words, the entire sphere that you're looking at is covered with light, or it's convergent, in which case there's a finite amount of surface that's covered. And so let's go back to my very first example. What if there was an infinite number of stars, more stars than you could count, and they're all lined up on a single line? You would not have the entire sky. The assumption is that the stars are distributed evenly, and that's not true. They're in clusters, and they're in galactic clusters. And this is one thing that's very interesting, is that every time we build a new telescope, we see into dark spaces where there's previously the biggest Earth-based telescopes could see so far into outer space and see galaxies, etc. But then when the Hubble went up, everybody went, wow, they could see all kinds of things. They took the Hubble Space Telescope, trained it on an area that previously had been thought was completely devoid of anything, and they found billions of galaxies. So just completely populated. And then when the James Webb Telescope goes up, they looked at regions which the Hubble Space Telescope, just looking through that, looked dark. And all of a sudden now you could see billions of galaxies and other structures that were never there visible before with the Hubble. So the end result, and let's answer the question, or make an attempt at answering the question, is the universe infinite in scope? And as science, this goes back to my original point of actually making measurements and using measurements and scientific data for answers, not mathematical hypotheses from people who sit in ivory tower offices. But the universe, no matter how many telescopes you build, bigger, better telescopes, you keep finding more. And so in terms of our ability to measure, that also goes back in time. The farther away they are, the fainter they are. That would imply that they're simply farther away, whether you use redshift or not. That's another whole story in itself, because the redshift is not due to things moving away from us. That's a whole nother subject. But the fact is that every time you build a bigger telescope, you see farther, you see more things, and that's the limit of our ability to measure. So you cannot measure, given the equipment, finite equipment that we have to look at the stars. You cannot measure the end of the universe. In fact, if you could take one of our telescopes, the James Webb Telescope, and move it out to the farthest galaxy that we can see, you would probably see that distance again off into the distance. So the universe, and these are staggering ideas, because the human mind is not capable of understanding infinities. That's why George Cantor came in. He put mathematical organization on infinities, something that had never been done before. So at any rate, the end result is that the stars are not evenly distributed in the sky. They're in clusters. So then how are those clusters distributed? They're distributed and they're very far apart. So it comes down to this mathematical analysis of does the, well, you could call it convergence. Is the universe convergent? In other words, are the stars close enough and numerous enough and cover enough area to where this concept should be true? Well, it's clearly not true because we don't see light coming from all regions of the sky. We don't see that. But then again, depending on the distribution of stars, we may not, even though there is an infinite number of stars. So, okay. Jumping back to the original topic there. Okay, so jumping back to the original idea of the Oort cloud. Now, the observation is that when comets come into the solar system, they have a limit to the outer bound of their, the distance from the sun, the outer portion of their elliptical orbits. The perigee and the apogee distances, of course, the apogee being close to the sun, the perigee being the distant point in the orbit, but concentrated around this region called the Oort cloud. But I propose that there's something very different going on here, and explains the data. So what happens, these comets are coming in literally from an infinite distance, but when they hit the solar system, when they form, that's the first time we see them, is when they become comets, and the little nucleus is just little teeny speck of rock out there. That is not something we are able to see with telescopes. So when they all of a sudden become a comet, the first thing they do is they attract material, draw it into the comet nucleus, and it slows them down. It's called the tail drag. I explain that in my work, in my books and publications. And so the tail drag slows the comet down and gives it the appearance that it's only coming from a certain distance, even though it really did come in from an infinite orbit, an open orbit. So it would be, you could call it an effect. And instead of the Oort cloud, you might call it the Makani effect. Put a name on it. Put my name on something. But anyway, that would explain the same phenomena that is measured with comets, but giving the correct interpretation. And also, it's provable, because you could, as soon as these comets ignite and become a comet, as they discharge the solar capacitor, if you immediately measure their orbital characteristics, then within a short period of time, you would notice that their orbits change to where they become a closed orbit because of the tail drag. Now that's the correct interpretation. Just like, for example, the correct interpretation of the microwave background radiation is that it is a cloud of dust and gas that surrounds our star, and that's what they're seeing. It's a microwave radiation, black body radiation that's of a cloud of material that's surrounding our star. And that is, by the way, the same material that is instrumental in creating the planets that are forming in the Kuiper belt. And the redshift that's coming from the all of these objects, galaxies, quasars in the universe that appear to be moving away, the redshift is not due to motion away from us, but it's due to an effect I discovered called the induced electric dipole redshift. It's the electrical properties around fusion-based stars, the non-uniform electric field, and photons moving through that reduces their energy and gives them all the redshift. And so that's what's going on. It's not due to objects moving away. So the end result there is a second source of redshift. And that is what we're seeing, not due to objects moving away from us. So the whole basis of the Big Bang, the microwave background radiation, and the redshift are due to very different causes. But this is what I get back to the original discussion of circular reasoning, that scientists begin with a hypothesis, it gains traction, and once it gets into the cycle of funding, publication, and monopoly of the system by power groups, then you're not going to change it, because they're going to keep going on. And literally recently, many scientists are finding all kinds of flaws with the Big Bang hypothesis, from the amount of very esoteric things like the amount of lithium in stars relative to the amount of iron. Very esoteric things that are predictions of the Big Bang that are not coming true, in spite of the fact that they claim that there is support, evidentiary support for the Big Bang. But there are so many things wrong with 50 years ago, we knew the Big Bang did not work. There were all kinds of contradictions, not the least of which is this nonsense about dark matter and dark energy, that they don't know what it is, they don't know what it looks like. There's because the universe is expanding, there are effects that they cannot explain with their models, so they have to introduce something that you cannot see or detect. And they haven't even defined what they're looking for. Can you imagine that? Can you imagine going on a trip? Say you took the family and you go on a trip, and you know, the wife asks, "Where are we going?" It's like, I don't know where we're going or what we're going to look for or what we're doing, but we're going on this trip. And so somewhat the same as the state of astronomy, astrophysics today, where they're looking for something, they don't know what it is. But the problem is there are a lot of other people who should be using that telescope time to make real discoveries, analyze real data, and get the scientific community back on track. A number of weeks ago, going to change topics a little bit here. A number of weeks ago, I talked about the Betz limit. I spent 3 weeks discussing aerodynamics, the Betz limit, and go back and watch those shows if you missed them. But I had a little bit to add on those particular topics. It's something I mentioned, but I didn't flesh out the topic. It's called reversible processes. Now, a reversible process is the one in physics or in chemistry in which you can go to a certain state and then say it takes energy to get there. Okay, so then if you go in the reverse, then you can get that energy back. A good example is the separation of oxygen and hydrogen from the water molecule through electrolysis. And then when you combine those back together, you get energy back. It takes energy to break them apart, and then if you bring them back together, you get the energy back. And of course, there's always some losses, but it's a reversible process. If you drive your bicycle up a hill, okay, it takes energy to get up to the top of the hill, but now you can ride your bike, coast down to the bottom of the hill and gain that energy back. You'll be moving at a higher velocity once you get down to the bottom of the hill. And so there's an exchange of energy there, but it's a reversible process is the point. So I want to talk a little bit about reversible processes. And one of the things when I talked about the Betz limit, which is this mathematical limit, how much energy can you extract from the atmosphere or from a column of water falling in a hydro dam? How much energy can you extract from the water? And there's a formula, it's called the Betz limit. And there's certain conditions on using the Betz limit mathematics. One is that you have some kind of non-compressible fluid, like in the case of a hydro dam, it is water. And so what happens is you have this column of water that's so big, coming down at a certain velocity, and as you remove kinetic energy, that's the energy of movement, the water slows down. So your pipe has to become bigger so to accommodate the slower moving water, so the same volume of water can move out the bottom, go out the bottom chute of the hydro dam. And then in the middle you have a propeller and impeller that is moving with the water, and as the water is extracted, the pipe around that flange is getting bigger because the water is slowing down. Now let's reverse that process. Let's say we're taking water from a reservoir down below and we're pumping it up to the top of the hill, back into the reservoir at the top of the hill. That is a reversible process. Now, if we had a 100% efficient storage mechanism for, say, electricity, then we could use the electricity and take the water that had fallen down, pump it back up, and then move it back up the same tube into the lake, and it would be the reverse, because the water coming in would be slow moving, and as it became faster moving, you would narrow the pipe down so that the same volume of water could move through the pipe up to the reservoir on the top of the hill, being a reversible process. So that's the crux of the issue now. Take a propeller, and specifically the three-blade wind turbines. It is not a reversible process. In other words, a propeller, on the other hand, is not a reversible process. What does a propeller do? You put it on the front of an airplane, you put a high energy engine on there, high RPM engine. It takes dead air that's not moving, spins and throws that air backwards and causes propulsion. Okay? Now, let's reverse that process. Take a fast-moving column of air, blow it on the propeller, and what's going to happen? Well, the wind is just going to blow through the three-blade wind turbine without really doing much. About 95% of the energy coming in that column of wind is just going to blow through the three-blade wind turbine without touching the blades or without doing anything. It is not a reversible process. Propellers are not a reversible process. So that's why the three-blade wind turbines are a dramatic failure. They don't work. And so this is when I invented the JMCC wing generator, I had to understand these things on scaling. How can you take something that, the reason small wind generators work pretty good is because they spin very fast. But the bigger you make them, the slower they go and the less efficient they become. And so when I was building the wing generator, I designed it so that it would overcome these problems. And the biggest thing I was after was scalability. In other words, how can you invent something that you can scale up to bigger sizes? And I give the example of the old clipper ships, the old cargo ships that used to cross the Atlantic Ocean before the ages of steam. If you are going to build a boat bigger and bigger, then the volume of the hull grows as the cube of the linear dimension, whereas the sails grow as the square. So you can put this enormous sail rig on these clipper ships, and they go really fast. So you can transatlantic trade, you can move your cargo across the Atlantic with sail in a hurry because of these big ships and because of the principle of scaling, making things big, and the fact that the hull grows at as the cube of the lineal dimension, whereas the sails grow as the square. Okay, and so the same thing is true of the wing generator, which grows in 3 dimensions. So as you make the lineal dimension bigger, it grows, the energy output grows as the cube of the lineal dimension. So it scales up to much larger sizes, whereas the three-blade wind turbine does not scale up to larger sizes. So at any rate, I wanted to get that in here about the reversibility of certain physical processes and how you have to understand these when you're dealing with engineering, especially things that are commensurate with dealing with, say, energy production. And looks like I'm about out of time again. We'll talk to you next week.
This has been Master of Science with host James McCanney. Join us each week as James will delve into historical figures such as Nikola Tesla, Albert Einstein, and the great mathematicians as we explore the history of man, Earth, and our universe as you've never seen it before. Tuesdays, 7 p.m. Eastern, right here on the Bold Brave TV network, powered by B2 Studio.